today. This is the second in the Vice Chancellor for Research seminar series. My name is Rob Duncan, Vice Chancellor for Research here. Our first seminar series was on One Health, One World, One Medicine, and that was held roughly 3 months ago. And we very much appreciate your attendance at this, either in person or online. Just had a few announcements before we start. For those who are attending in person, the restrooms are just straight out the way you came into the lobby and to your right. Beverages, if you'd like to take a break from the proceedings, there's Starbucks that closes at 4 p.m. that's in the main lobby just across to the other side of Memorial Union. A vending machine and sodas ATM are also located nearby. For those who are, since we're not providing lunch, those who are interested, McDonald's is just outside the Memorial Union to your left. Okay. Let's see. I wanted to mention that we had one paper by Dr. Jeff Holks, who was interested in presenting his work. We have a few copies at the back of the room. We've also posted it online at the research.missouri.edu website. Let me ask everyone, please turn off your cell phones for this event. And one thing, this will be web streamed with the agreement and permission of all the authors. So since this is being web streamed and recorded, if you are interested in asking a question, we'll have 25 minutes for presentation per author, 5 minutes for questions typically. If you're interested in asking a question but you don't want to be on the web recording, please feel free to write out your question. Pam and here in the back of the room will be glad to take your question in writing and hand it to me. If we have time at the end of the 5-minute period, I'll make sure that we ask the question. If we don't, if we have overflow, then I'd encourage everyone to talk to people individually afterwards. Okay? Let's see. I think that completes our announcements. So with that, I'll go on and make the first presentation. The talk I'm planning to give is Prospects for the Discovery of New Energy Science. And this is something similar to what I presented, but a little bit more detailed when we had the Missouri Energy Summit a few weeks ago. Now, one question I've always had, and I've often called this cold confusion, just because for the last 20 years there's been such a flurry of, I think, sometimes confusion about this topic. But I was kind of surprised there was such a surprise in 1989 for two reasons. The first report of a possible nuclear fusion reaction in palladium loaded with heavy hydrogen, to my knowledge, was reported in Berlin, Germany, September 17, 1926, by Paneth and Peters, as listed here. I think there had been, for quite some time, some understanding of potentially anomalous effects happening in deuterated palladium. But as we'll see in a second, this came as, I think, a large surprise to everyone in 1989. The other reason why I'm surprised is that there's detection of confirmed nuclear fusion in liquid heavy hydrogen near absolute zero temperature in Russia, Berkeley, and many other places across the 1950s. And this is fusion catalyzed by naturally occurring flux of a lepton called a muon. I'll discuss in just a moment. Now, the possible free space nuclear reactions that have been suggested for this possible fusion effect is deuterium plus deuterium goes to helium-3 plus neutron plus the energy shown here, or to a proton plus a triton plus, again, energy. Or, very, very rarely, these first two reactions occur at about equal probability, but very rarely it goes to helium-4 plus a gamma ray, electromagnetic radiation, at 23.8 MeV. And this only occurs in free space about one time in a million because the phase space for a light ray, a gamma ray, to conserve momentum with the helium-4 is very, very narrow. So that's why it's typically not a reaction that's routinely seen more often. There are also possibilities of deuterium interacting with tritium, hydrogen-3, and forming helium-4 plus a neutron, 17.6 MeV, or a proton plus deuterium going to helium-3 plus gamma, again with that energy associated. So these are the reactions that have been, in fact, observed in liquid hydrogen from muon catalysts, and also these reactions have been proposed to be possible fusion reactions in cold fusion in palladium. But now returning to the possibility of muon-catalyzed fusion. This was the paper published by J.D. Jackson, the same person who published the textbook on electromagnetic classical electrodynamics that many of us have taken as graduate students in physics or in engineering. He gave a great paper, one of the best I've ever read, on the catalysis of nuclear reactions between hydrogen isotopes by mu mesons. Now, mu mesons are not mesons, are leptons, and they're typically 207 times more massive than an electron. They have a 2.2 microsecond half-life, and they shower the Earth at an average rate of 1 per square centimeter per minute. But they come in at about 3 GeV, 3 billion electron volts, very close to the speed of light. Now, in the case where the muon slows down enough to cause molecular recombination, the muon can displace the electron and form a d mu d molecule. And it typically forms in a fraction of a microsecond when the deuterium is at liquid D2 densities. It's interesting to notice that the deuterium loaded into palladium in the experiments that will be discussed through the day today typically are above the density that you should typically find in liquid D2. And so you'd expect the molecular recombination time to be at least equally fast. And when this forms, the muonated D2 molecule, the spacing between the deuterons is only about 0.5% of what it is in naturally occurring D2. And a vibration period exists of about 5 attoseconds, or 5 times 10 to the minus 18 seconds. Each time it vibrates, on its close approach, there's a tunneling probability across the Coulomb barrier that gives a substantial probability of fusion. And again, after a sufficient number of vibrations, a fusion often occurs. Each muon will typically catalyze about 10 D plus D nuclear fusions before it combines with a positively charged fusion product or decays. And typically, in the D plus T reaction, the muon can catalyze about 100 reactions. Notice, this is cold fusion, no doubt, really cold fusion. I'm a low-temperature physicist, and this is starting to be what I'd call cold at close to 20 kelvins. But no energy technology impact, since muons are so expensive to create artificially, and since their natural luminosity is far too low. So there has, in fact, been the observation of cold fusion before. Now, let's talk about, again, the cold confusion that occurred in 1989, but now in the age of new media, and I think this is significant. Pons and Fleischmann from the University of Utah held a press conference in March 1989, and arguably this was, in my opinion, very bad media strategy. There are a lot of promises to this solving the world's energy problems on the first appearance of an exciting new scientific observation. When this did not repeat, and when Pons and Fleischmann had trouble repeating their own work after they ran out of a controlled lot of palladium that they're working with, there was a very, very negative reaction by the physics community worldwide, but especially in the United States. And at that point, real science, with possible profound engineering consequences, suddenly became a pariah science. I mean, I've had a number of grad students and postdocs. I would never consider, say, suggesting to them over the last 20 years that they go into this field. And that's a real problem. Because, again, there's something to explore here that hasn't been explored. And I think it's interesting to note in the 60 Minutes show on April 19, Professor Fleischmann expressed 2 regrets. One was that he held the news conference at, he says, the University of Utah's request. So again, I think acknowledging the media strategy had a negative impact. And secondly, for calling it fusion, because again, it's a fascinating new effect, as we'll discuss, but the physical origin had not been clearly determined at the time of the conference. Now, since that time, about 200 excess heat measurements have been made by many independent labs that essentially repeat the Pons and Fleischmann results in the 2 decades that have spanned since the time of that initial report. And so these 200 observations are often have been made by people from very esteemed laboratories, very, very accomplished experimentalists. So there's a persistent observation of the same kind of confounding effect. Now, the 60 Minutes story that aired on the 19th of April, I reported on a visit to Energetic Technologies, a company in Omar, Israel, that's owned by a U.S. firm. And in that, I was asked to determine whether the excess heat was, in fact, experimentally defendable, whether they were seeing excess heat in a way that was compelling. And so I observed a cell creating excess heat while I was there. 3 different cell designs were used, all very different, and all of them have reported, according to Energetic Technologies, excess heat in the past. 5 cells have reported excess heat exceeding 1 megajoule, and again, realize this is a 0.3 gram palladium foil electrode typically. Chemical heat release would have been in the range of, say, 100 to 800 joules, and heat out to energy, electrical energy in, has been as high as a factor of 25 or 15, and those are rare events, 8 is more common, and smaller values are far more common still. And quite similar results have been seen in other labs in Italy, Russia, China, Germany, and the United States. Here in the United States, we'll see presentations from experimental results at SRI and by the Navy SPAWAR. Now, let me just quickly say what's being measured. Essentially, electrical power is supplied to this cell, and the cell consists of a palladium cathode and platinum anode, and a number of thermometers are shown here. The thermometers essentially convince us that the thermal gradient points back towards the palladium, so it really is the source of heat. It's not a volume effect or something of that nature. Now, the power in at any instant in time is simply the current that flows between the cathode and anode times the voltage difference, V. And the situation is that when this power is put in, there's electrolysis, and when the electrolysis occurs, the hydrogen and oxygen go up towards a recombiner that are outside the calorimeter envelope. And when that occurs, there is recombination, and some heat that's applied actually escapes through the external recombiner. When I went to Israel, I was very concerned about systematics for how they accounted for this effect. And what I saw was they, in fact, ignore it. So they say whatever heat escaped from the recombiner was just involved in that escape, and there was no attempt to correct for a lower effective net input power based upon the recombiner escaped heat. Now, the way the heat out is measured is simply a thermal conductance factor times the temperature gradient between the region where the cold fusion is supposedly occurring and the liquid helium, or I'm sorry, the liquid water bath at T5, which is combined, which is regulated quite effectively to within a small fraction of a degree Celsius of its operating temperature. The excess heat is just the output heat minus the input heat. And by the way, a time-varying waveform that energetic technologies call super waves is used to do that. Clearly, a time-varying waveform is much more effective at loading the palladium with deuterium. And the excess heat is just the sum over all time intervals of this excess heat times delta T. Now, I should just mention that other methods like this, which were a deuterium plasma that accelerates the ions to crash into the palladium, was used as well. And this is a similar type of experiment, except now there's no electrolysis involved. It's in fact bombardment by ions through a rarefied cell where the pressure is typically as high as at most 20 millitorr. And the point here is that this calorimeter is different. Instead of waiting for steady state and taking the difference of the temperatures multiplied by a conductance factor that's due to the alumina, in fact what happens here is you're looking at the raise in temperature T out minus Tn times the flow heat capacity of the water times the flow rate to give the amount of heat that comes out of this. The heat that goes in is the ionic current of the deuteron ions times the voltage difference that they fall through before they smash into the palladium. So this is, again, one of the other methods that was used at Energetic Technologies. Again, very different systematics. Now, the interesting thing is that, again, at Energetic Technologies, there was a run in 2004, of course, well before I was there, and this shows the temperature traces from all the thermometers that observe this effect. Now, this is drawn to scale. Typically, most of the heat will go through this gap that's 1/10 in size, the gap that exists at the ends. So end leakage effects are fairly small and computable, both on the bottom and top. But most of the heat that diffuses out of this will occur across this thin layer of alumina. But now the situation was, in this run, you see that there was substantial temperature rise, considerable temperature rise, up to 34 to 50 degrees Celsius above the bath temperature. And then all of a sudden, it went up to 100 degrees, at which point it started boiling the electrolyte inside the cell. And over this period of heat release, then it eventually came back down, stayed at very, very high excess heat levels. And it's interesting that the bath that kept the equal temperature conditions around this actually showed a bump because the excess heat from this exceeded the ability of the bath refrigerator to compensate. Now, in the calibrated range, there was a documented heat release of 1.1 megajoules, according to Energetic Technologies. And the estimate, based upon the electrolyte boiling in the uncalibrated range, is that the total amount of excess heat could have been as high as 4 megajoules. Again, remember, a 0.3 gram electrode, and this was about a times 25 release of heat in comparison to the amount of energy that was placed in electrically. Now, there are many other results. There's been heavy loading with palladium is required. So the interesting thing is that this is clearly dependent upon the palladium metal in ways that are not yet understood. Heavy loading, such that you have to have almost a one-to-one loading of deuterium to palladium to see the effect. And again, Michael McCoubrey will discuss, I'm sure, some of that. That was what he had seen. And this looks probably like it's a surface effect. It may depend on deuterium deposited in voids as well as the deuterium reacted with the palladium. That's yet to be explored thoroughly. And it's also, this clearly can be improved by surface roughness, again, empirically. Surface depressions, ultrasound-induced surface roughening have been seen at energetic technologies to favor a greater heat release and a shorter onset time. Careful surface studies are ongoing now at the Naval Research Labs and other locations around the world. Many different methods of loading have been done. We've seen electrolytic, we've seen the ion bombardment. There's also been D2 gas pressure loading of zirconium palladium nanoparticles in Arata's lab at the University of Tokyo in Japan. And this has shown excess heat every time, according to their group, and the onset time is typically very short. Co-deposition technique that we'll hear about, that's been developed primarily by the Navy Spay War, or exclusively by them, has been developed for electroforming, again, the palladium with the deuterium that's liberated in situ. And this is also reported essentially either particle tracks or excess heat when excess heat has been explored for at every time that it's been checked for that. All have displayed excess heat, and I think that's very interesting. This excess heat release is quite variable, often onsetting from 10 to hundreds of hours after the deuterium is loaded. And it is occasionally 10,000 times higher than would be expected by chemical origin. The amount of heat release and the onset time are quite variable from run to run. And gas pressure-loaded nanoparticles in co-deposition both report excess heat in the case of co-deposition when that is checked for every time, while others are less likely, sometimes like electrolysis was reporting maybe one time in 7 or so. And again, is this excess heat effect real? Well, when I went to Israel, I asked specifically in cells that were electrolytically loaded whether there were recombiner concerns that I mentioned before. And essentially what they did was they just took care of that concern by underestimating the excess heat, by pretending as though none escaped from the recombiner. That's, of course, the most conservative statement they could make of their excess heat that they've measured. I thought that could be an area for systematic, but in fact, the excess heat reports by taking this convention for PN are underestimated. Volume chemical reactions. Question is, if you had, say, a leak of oxygen into this and you're liberating, say, deuterium at the cathode, could it be re-reacting with the oxygen and creating, say, an excess heat effect from that effect? And essentially, two things. One, this excess heat effect isn't seen until long after this thing's fully loaded. And so when it is fully loaded, you could always argue, well, could the deuterium being diffused out of the palladium reacting with the oxygen some later time, many hours later? Well, that would give at most about a kilojoule of excess heat from a 0.3 gram palladium electrode, certainly not at the occasional megajoule and likely 50 kilojoule levels that are typically reported. And now, ground loops or shorts. An isolation transformer was used in measuring the cathode resistivity to determine the loading. Other methods of obvious ground loops that could have occurred did not appear to be there. And generally, I'd say that this lab, and I think many others that are working in this area, practice extremely good laboratory technique by very qualified experimentalists. An underestimated input power. An electrolytic interrupter effect was mentioned by primarily Professor Garwin, and I thought it was a very reasonable thing to be concerned about. Typically, there's a 50 kilohertz measurement system sampling rate, and typically about a 20 kilohertz bandwidth for the measurements. But the question is, since you have an electrolyte against electrodes and you establish a strong loading current, could there be oscillations that occur, electrolytic oscillations that have been observed before in things like spark gap transmitters? Well, direct measurements with a 200 megahertz scope, both looking at the current and voltage, indicated that this was not the case in these experiments. And to the level of the measurement of the oscilloscope, any such effect that might occur below the noise level of the oscilloscope to detect would be less than 0.01% of the near DC power input from the superwave source, as they call it at Energetic Technologies. So this was a reasonable thing to wonder about, but again, by direct measurements, it's not a substantial concern. And then there's a proposed calibrated physical source measurement by Professor John Reppy and by Professor Garwin, Dr. Garwin, of doing a measurement with like a capacitor bank or a dynamo where we could actually see the energy that comes out of the controlled source that goes into loading the cell. I think that would be a very useful experiment to do, but I think the situation is that this direct experimental evidence is compelling that the electrolytic interrupter effect was not actually causing us to, or not us, it wasn't my data, it was Energetic Technologies, that it wasn't causing Energetic Technologies to substantially underestimate the amount of input power. Now, there we go. So I conclude the excess heat effect appears to be real, and I'd say that very strongly. Even if the input power is mismeasured due to an electrolytic interrupter effect or something like that, why didn't it appear on the 200 megahertz scope measurements? And even if it did, even if for, say, many, many hours during the loading, you're in fact applying more power than you think you're applying, what physical mechanism can store 50 kilojoules to 4 megajoules of energy near a 0.3 gram palladium electrode for heat release a few hours or days later? Nothing that I can think of. I think it would be pretty amazing if there were such a mechanism. Now, even if some amazing new mechanism like this were present, or were to be discovered, it would be absent in the other methods of loading that don't use electrolytic techniques. And all of these other methods of loading report excess heat. So I think we're very safe to say the excess heat effect in these experiments is real. Now, again, here are the calculations that show that we expect it's far greater than the heat release that would be available chemically. The enthalpy or heat of reaction of palladium with deuterium is about 43 kilojoule per mole. Remember, you have a 2 millimole palladium electrode. And so about 100 joules or so would be released if somehow that heat release could be delayed by hours by, some type of delayed chemical reaction of the deuterium with the palladium, which of course itself is extremely unlikely. But nonetheless, if it were that chemical origin, about 100 joules. And how about if there were an oxygen leak? Okay, that produces around 250 kilojoule per mole of heat. So for 2 millimoles, if this is, say, hydrogen coming out of the electrode, then maybe 500 joules of delayed heat release would be observed. Now, many measurements show, again, typically about 50 kilojoules of excess heat release, occasionally over a megajoule. And it's usually from ambient temperature to about 100 C, with occasional reports of heat release at extremely high temperatures, approaching and in fact exceeding the melting temperature of palladium. Now, it's interesting to note, just to kind of give a feel, it's not uncommon for a laboratory that's doing this research to see these levels of excess heat release at about 50 kilojoule level, many times in a month. But typically these labs see these incredible excess heat releases, often exceeding a megajoule, typically maybe once a year or so in steady operation and considering many different cells. So again, the whole process of the palladium and the materials science is not yet understood well enough to understand what's making this big difference, although very exciting research is continuing in that as we speak. So what's going on? I think basically we don't know. It's going to take a lot of experiments to figure this out. But since the excess heat appears to be real, this is enough to motivate serious study. Remember, this is an empirical science. There's some interesting observation here. And so I had a hypothesis initially that I don't think is really can explain the whole effect, but possibly ignition through muon-catalyzed D+D. And microcraters were found in the palladium surface in ET and in the Israeli company and by Navy SPAY-WAR, and they look quite similar, in fact, and I think that's interesting, independent labs seeing similar features. And there are, of course, after me, there will be reports by SPAY-WAR for the first time of these very exciting particle track production. Very little U.S. public funding means that there is very little assurance that the results that come available from this area of results will reach the public domain. It's been estimated about $100 million has been invested in the 2 decades since Pons and Fleischmann's announcement. Well, that's kind of problematic because, of Of course, the big advantage of publicly funded research is a requirement for public disclosure, and also the government keeping a non-exclusive license typically to any patents that come from this. So we were in a pinch once when the transistor was developed at Bell Labs in private money. Later, negotiation had to occur to make its use available more broadly than just through one company. So again, I think it should be an area, at least with some more public funding. And to my knowledge, the only U.S. public funding in this area of research has been the DARPA funding that's occurred recently, to my knowledge. Now, muon-catalyzed ignition, I won't linger on this, but basically, this hypothesis of muon-catalyzed ignition could occur, but again, what it would describe is in the electrolytically loaded cells, you'd expect maybe a 10-hour average arrival time for an ignition muon. Again, this makes assumptions about the nature of the palladium. And this could qualitatively describe the onset time and the excess heat release being so variable, dependent upon the palladium preparation. But it would not describe how the nuclear reaction is sustained, or why muons and tritium are absent, or why the gamma is absent if the D plus D goes to helium-4 plus gamma is favored. 2 minutes, great, thanks. So there are evidence for nuclear process. Again, I think some of the most compelling is this work by Spavor that we're about to see. And then there's a question, because of the general absence of many particles. Again, Spavor will show some particle production, but it doesn't appear to be at the levels necessary to describe the excess heat measurements. And there's a process where this could go to helium-4, and the energy could be hypothetically taken up by the lattice, and the momentum's conserved by the lattice. But this is something we've never seen before. The Mossbauer probability is so low, it's not a Mossbauer effect like has been studied before. But are there other possible quantum coherent mechanisms? And again, Professor Kim will be discussing some of that today, as I think also Professor Egelstein. So more complex nuclear processes are something we totally don't understand are possible as well. Here is an image of these microcraters that were seen by energetic technologies. And again, they hypothesize these are due to extreme heat release in the palladium surface. And then again, they've seen other examples of these many times. They do tend to correlate roughly with the electrodes that produce more excess heat, but there hasn't been an aerial study to really quantify that in more detail yet, to my knowledge. I think it's an area of exciting current ongoing research. And again, Spavor will show, I believe, this, and this shows where they've also seen these craters that may be, in fact, formed by intense heat release that could be coming from a nuclear process. Lessons learned here, okay? There's a huge gap between new science discovery and useful engineered systems. Don't speculate it wildly. Manage expectations, okay? Pursue basic research because we don't understand. We really don't understand what's going on, and it does appear to me the excess heat is quite real, so that should motivate serious study. And I don't know if this will ever lead to energy production, but that's natural at this stage in the development of this. It's extremely important to find out systematically if it will, in my opinion. Mass media needs to approach new discoveries carefully in light of the first point above. Research funding needs to become less dependent on the common assumptions within the culture of scientific communities, more courageous and objective. And I'd say the scientific method is a truly wonderful thing, and it should be used always with no exceptions. Well, with that, what I thought I'd do is stop, and do I have any time for questions, or have I burned time? Okay. Well, if I have a minute or two, what I'd go on to say is that this question of junk science versus empirical data, persistent observations like what we've been discussed here and examples of superconductivity above room temperature have been reported by very capable groups many, many times. And instead of just discounting this as junk science, it seems to me much better to take this as an empirical clue that our understanding is incomplete, which it probably always will be. That shouldn't be a point of any embarrassment. Science should go after what it doesn't understand. And the scientific method is the only thing we really have. Unfortunately, it's the only thing we need. Media and science don't mix well, okay? I think adaptation of scientific communities to mass media generally drives science away from open inquiry for the scientific method towards showcasing accomplishments in an attempt to win competitive resource allocations, okay? Peer review is slow, but can be very valuable, especially when associate editor appeals are permitted. Extreme peer pressure to conform to accepted funding norms, I'm sure, has blocked important publications, but I think it's rare. So I think we should continue to embrace and strongly support harsh peer evaluation of our research at every stage. And path forward, I would recommend an empirical approach to see if this scales according to the tested according to the scaling hypothesis, and pursue all applications. Does it scale? If how? And basically, will this ever lead to something that produces at least 350% excess heat reliably at adequately high temperature for efficiency energy conversion? So this is more the empirical approach. Is this ever going to be a reliable source of new technology for energy? And then the second is explore for the fundamental mechanisms. Even if the answer to the top is no, there's something fascinating going on. Understanding it will be very important to our understanding of both condensed matter physics and nuclear science, in my opinion. So, at any rate, with that, if there's still time for a question or two, I'd be glad to. And again, if people here, yes, please.
My understanding of what you said is that there's consistent heat production.
Yes.
Excess heat production. Is there consistent?
Excuse me, if you would come to the microphone because we're web streaming, that way the entire audience will be able to hear it. And the answer to.
Oh, yeah.
And the answer to would have to be in the microphone.
Right, right. And also, if you'd rather not go on live on your question, feel free to provide it written to Pam, and she can give it to me in paper so you don't get online.
Surely. My understanding was there was consistent excess heat production. Were other artifacts, or not artifacts, ramifications of the process also consistent? Were there always certain products formed? Were there always the same levels of energy? Were other things
Right.
consistent, or was it just all over the map at that stage?
Right now, all over the map, I think, is the best answer. Well, there were, in fact, you'll see in the next series of talks, evidence of particle production as would be expected, but it's typically much lower in level than to explain the excess heat reports. So it appears to me that there's something we really don't understand here. And again, the fact that the empirical evidence shows excess heat production well above the levels that we'd expect for chemical heat production is more than enough reason to pursue it seriously. But basically, you'll see in the upcoming talks that where some particle production has been seen as expected, it's typically at levels lower than what would be able to account for the excess heat measurements. Any other questions? Or in that case, our next presentation will be by the SPAY work group. And for that, I believe we'll be starting with Frank. Very good. So the next presentation will be by Dr. Frank Condon, who's head of Research and Applied Sciences Department at the U.S. Navy's SSC Pacific Laboratory. And Dr. Gordon, I'm sure, will introduce the other two members of his team here today for this presentation on the Navy results.